Okay, everybody, what's up? Let's do our usual audio test. Yep, that works. All right, so let's get into it. All right, this is the end. This is the last week of it. So we're gonna get our final material, 5.2, 6.1, and then we'll do 2 more homeworks, which I have shortened, so they're a little bit more manageable, hopefully. And we'll take our final exam, which will have like a few explicit kind of computations, but generally be a little bit more conceptual, at least towards some of the later stuff. I won't expect you guys to have mastered everything in 6.1, like on some deep technical computational level, since you'll have seen it not that long before you'll be tested on it, right? It's always the difficulty of the end of classes. You know, you want to teach upright till the end, but anything that you do right at the end, you sort of feel like you can't test over. So it'll be more our discussion of the end of this information after we finish 5.2 here today. In 6.1, this last bit will be more conceptual and just kind of trying to, like, you know, close the loop on what we've been doing, while also leaving open the wide and interesting world of complex analysis to hopefully pique your curiosity and keep you studying and engaged in the discipline after the class is done. Sorry, I had something in my throat there. All right, so last time we were getting into, also before I start to go on this, exams are back. They are in the computer and everything is graded there. We are current on the grades, so please check your grades. If you are concerned about them, please let me know. Talk to me soon. We are down to the last week of class. If you have left it till now, I have encouraged you to not do that, but you still should talk to me. Don't give up just because it's right at the very end. Anyways, so last time, also if you look at your exams, please do double check that I didn't make any addition errors or anything like that. I do always try to go over them a couple of times to make sure I added up everything correctly. But when you're punching grades in for a few hours, you know, it can be pretty easy to accidentally fat finger like a 15 instead of a 5 or something. Or, well, if I did that, then you don't have to tell me, but it's easy to fat finger a 5 instead of a 15, right? Like, you know, it can happen. So anyways, let's get back into it. Fractional, linear, and Schwarzkristoffel transformations are what we were talking about last time. We had just gotten into talking a bit more about conformal maps in 5.1, and we started to discuss more of what this geometric thing that analytic functions do is, at least the geometric thing that analytic functions do near points at which their derivatives are non-zero. So this conformality property was pretty interesting. We got into various notions of conformal equivalence and what things are equivalent to other things. And one of the things we got was the Riemann mapping theorem, which said that a simply connected region, you can map it into the disk. And so we said, okay, well, let's start to study some of these conformal maps. And one of the ones we started with was fractional linear transformations, otherwise known as Mobius transformations or bilinear transformations. These are mappings of the form TZ is AZ plus B over CZ plus D. And we're going to also assume that AD minus BC is non-zero, because in that case, we just ended up with a constant. So we talked about these guys. We said, hey, if you have a map T that's defined as one of these Mobius transformations, one of these fractional linear transformations, then it's bijective and conformal when you look at the appropriate domain and codomain, and it has an inverse that is also a fractional linear transformation. Okay, cool. We went a little bit further, and we started talking about, hey, well, why do we care about these guys in the first place? Well, returning to the Riemann mapping theorem and how we were establishing the conformal equivalence of certain regions to the open unit disk. We then went to say, hey, well, what about the conformal equivalence of, like, the open unit disk to itself? What are the maps from the open disk to itself? the conformal equivalences of this type. And it turned out to be that they were all fractional linear transformations of the form tz is e to the I theta z minus z naught over 1 minus z naught bar times z for some fixed z naught in the disk and theta in the interval from 0 to 2 pi. And all of those maps are conformal, obviously, and all of the conformal maps are from the disk to disk are of that form. So that was pretty cool, and that was kind of a big deal. We also last time, just to refresh our memory, got a little bit of an idea. Oh my gosh, my tablet is going crazy right now, so hopefully this doesn't go south. We got a little bit of an idea about what these guys actually do. So remember, conformal maps just can be broken nicely into 4 little pieces. You'll deal with this in the homework to actually show and verify this is the case, but this is a good way to think about it. The first one is it just shifts z, just moves it over, translates it, adds d over c. The next one is it inverts. That is, we just take the Riemann sphere, the 1-point compactification of the complex plane, and we flip it inside out. We turn it inside out, just like a balloon or something, right? Then the next thing we did is what's called a homothety, and I got a question about this, so I want to address it. So some people pointed out that, hey, look, this is just like a constant, right, times z. Why is this some weird transformation? Is it because of this form bc minus ad over c squared? Is that important somehow? No, it's because homothety is that is the type of transformation that multiplying by a complex number is. Namely, we know that when you multiply by a complex number, you rotate by, multiply by like some number by like z, right? Then you or I should say like by w, multiply z by w. Then you're going to add the argument of w to the argument of z, so that's like a rotation, and then you're going to multiply the moduli. So we're going to just scale it up or down, right? So that's what's going on, is we rotate and then we scale up or we scale down, and that's what a homothety is. This nice 1-point perspective thing, that's the scaling piece, and just like a rotation along with that. So then the final thing is we just do another translation. So just move the complex plane a little bit, flip that sphere inside out, scale up a little bit, just multiply, just a simple multiplication really, and then move it again. So these guys aren't really too bad to understand intuitively in terms of what they do. And I think people can kind of get wrapped up in having this somehow seem difficult or weird just because they have, I don't know, honestly, probably just because they have cool names, right? Like a fractional Mobius transformation. What does that even mean? Nothing scary. So let's get into proposition 5.2.3, some new stuff. This guy, we're going to start to get into some of the additional nice properties that that fractional linear transformations have, in addition to being nice things like the only possible ways to map a disk onto itself conformally. So here's another nice property. Proposition 5.2.3, and the niceness of these properties, by the way, should be kind of apparent from that decomposition into 4 simple pieces we just talked about. All of those are very easy, right? It's like move it, flip that, invert it, then multiply by like a complex constant, do a homothety and a rotation, and then do another move it. Easy, right? So those are all very nice little transformations, so we should kind of expect nice properties. And here's one of them. So let's let T be a fractional linear transformation. Now if L is a subset of C, that's a straight line, and S is a circle, then T of L, that is the image of that line, is either a straight line or a circle, and T of S is also either a straight line or a circle. So this is kind of obvious actually if you just think about the decomposition we just did. So take like a straight line or a circle, move it. Is it still a straight line or a circle? Yep. Okay. Then flip that sphere inside out, Now maybe something has happened there, but that's an interesting step. Think about it real quick. Maybe that's like an interesting place. But then afterwards, we're going to multiply by a constant. Is it still a straight line or a circle? Yep. Then we're going to move it again. It's still a straight line or a circle, right? And in fact, if it starts with a line, every step right there, except for inversion, keeps it a line, right? That is, if you have like, you know, like y equals CZ or something, you know, right? CZ is like a complex line, right? A constant times a you know, right? Yeah. So, anyways, that's everything we do, you know, is we're just moving it around, multiplying it by constants. We're going to keep lines and circles, except the inversion step where we maybe will have things like wrap around nicely if we've moved things around in certain ways. So anyways, let's keep going from here and see some more properties that we get out and kind of finish this off. The nice piece, this next nice piece is the cross ratio piece. There's a problem on your homework about this. So 5.2.4 cross ratios. So in line with what we just did, I'm going to actually skip ahead before we give this little theorem right here. Here's kind of the idea. So if you have 3 points, either those 3 points are collinear, right, all on the same line, or they're not, and in which case you can make a circle that goes through those 3 points, right? Kind of verify it to yourself if you don't believe it. But just think about the fact that you can make like a little triangle with any 3 points, and you can imagine the circle with those points inscribed on it, right? And so, you know, similarly, if you have 3 points that are all on a line, it's pretty easy to tell what that line is, right? Okay. So anyways, this is the idea of what we're going to do with cross ratios right here, is that this notion of, hey, the image of a line or the image of a circle under a fractional linear transformation remains a line or a circle, right? What we're going to do is we're going to essentially measure that to some extent by looking at 3 points. And then we'll actually generalize this a little bit with a slightly more interesting type of transformation called the Schwarzkristoffel transformation. So the cross ratio. Okay, so given 2 sets of distinct points, z1, z2, and z3, and w1, w2, w3, so that is, we're saying that z1 is not equal to z2, and z1 is not equal to z3, so all of these guys, and z2 is not equal to z3, you know, same stuff with the w. You guys understand what the word distinct means, right? So distinct, but of course you could have z1 equal to w2 and so on, right? Like it's not 6 distinct points, it's 2 sets of 3 distinct points. Okay. So given 2 sets of 3 distinct points, there is a unique fractional linear transformation, let's call it T, taking zi to wi for I equals 1, 2, 3. And in fact, if tz equals w, then here's the nice piece. So you could think of this like tz minus w1 over tz minus w2 times w3 minus w2, w3 minus w1 equals z minus e1. Sorry about that. Z minus c1 over z minus c2, z3 minus c2, z3 minus c1. So notice, if you want to kind of write this in a slightly different way, this piece right over here, this is just tz minus, now if w1, right, this is t of z1, right, over tz minus t z2 times this piece right here. I should have actually, here one second. This is the nice thing about doing things digitally. I can give myself a tiny bit of extra room when I need it. All right. Oh. And then of course times tz3 minus tz2 over tz3 minus tz1. So notice, this piece here compared to this piece here, notice I've just put t's on everything, right? That is, these ratios remain the same, right? So the ratio, this nice piece right here, it is essentially preserved under the fractional linear transformation, which honestly makes sense because it's like a fraction of lines, right? And these are all lines, right? Okay, anyways, I'm not trying to belabor that point too much, but there's a unique one that takes zi to wi, so tzI is wi, and this nice fact holds. All right, easy enough. So you can use a fractional linear transformation to map any 3 points to any other 3 points. That's kind of the takeaway, the cool piece. Now, 3 points either lie in a unique circle or a unique line. That is either 3 points. Take a line between any 2 of the points. Does the third point lie on that line? If it doesn't, then make a circle. You can always, like, you know, if you have like 2 points and then like another point like way over here, right? You can always like imagine. I'm gonna do such a bad job of drawing this circle. Let's see. Oh, I actually got pretty close, man. Oh, it's gonna be like a weird ellipse. You can imagine if I, here, I'm gonna make this a little bit better, okay? So if I take this, there we go. Sorry, that's what I was trying to draw. You get what I mean, right? So, you know, here's 3 points. Like, in case you felt deceived by the picture up here where it's like, hey, those look all like nice, like an equilateral triangle. This certainly doesn't, right? You know, you can always put a circle through 3 points. I just can't really draw circles freehand that well on a tablet, right? And you can always do a circle through 3 points that aren't all collinear, right? All on the same line. And so that's the business, is you can send any 3 points to any other 3 points and you're good to go. That's the whole business. So being able, how to do this though is slightly more interesting. You should think about how to do it. It is described in some more detail in your book, but it's pretty easy to get there if you just go through from the definition. There's not that much to solve for, but I'd encourage you to try it. You'll see a whole lot more of this, and you'll get to deal with exactly the cross ratio business in the homework, so I won't spoil it right now. But that's a cool piece. Anyways, the next type of transformation is the Schwarzkristoffel formula. So this guy gives an expression for mapping the entire upper half plane or unit circle to the interior of a given polygon. That's kind of nuts. There's kind of a lot of polygons, right? You know, just like areas you could enclose with lines between points, right? Now, this piece we'll do is for the upper half plane. The circle piece is an exercise in the textbook, and you can see that if you want. I will not make you do it in your homework. So let's talk about the Schwarzkristoffel formula. The Schwarzkristoffel formula, this is proposition 5.2.11, just another good example of a conformal map. So suppose that P is a polygon in the, let's call it in the W plane with vertices W1 through Wn. That is, if we're looking over, there we go. It's these guys, right? The W's, the vertices, right? Okay, so these are the vertices of our polygon, and the exterior angles are pi times alpha I, where alpha I is between 1 and -1. Okay, so we're basically going from minus pi to pi instead of from 0 to 2 pi. Think of it like that. And so these are just the exterior angles, that is the angle, you know, like if you drew the line between W1 to W2, right? and then, or, you know, wi to wi plus 1 and wi minus 1, right? Sort of, right? Like it's easier to see with 2, 3, and 4, right? But, or even just here at 2, between wi and wi plus 1, right? Or wi and wi minus 1 and wi and wi plus 1, right? And then you look at the intersection of that line, look at that angle right there. You can see the picture. It's straightforward enough. You know, if you actually want to state it in terms of how you're getting those angles, it would probably be a little bit more annoying because you have to think about, you know, like W1 minus 1 should then be W5, right? W0 is W5 in this case. So all the same. You guys can see the picture. Those are these angles, or at least they're the angles divided by pi or something, right? At least for like the angle is living in the minus pi to pi strip. Okay. Now, then the conformal maps from the upper half plane, that is this guy here, onto B, the interior of P, that is into this region inside of this polygon, they have the form f of z is a times the integral from z0 to z of zeta minus x1, that's a point over here, to the minus alpha 1, times so on and so on, all the way up to zeta x n minus 1 alpha to the n minus 1 d zeta plus b. Oh, okay. So, whoa. Now, obviously, the a's and b's are some constants, and those guys we'll talk about more in just a moment, so you can get some more intuition. And the integration will be along any path in A that is in this upper half plane, adjoining z0 and A to z. So some point z0, right, to z, wherever the z is, right? Pick up point z. What does this map send z to? Well, you're going to use some path going from some initial point to z, whatever path you want, you know, some gamma, I don't know, right? The integration is along that path, right? So really we should say like along gamma. This isn't just, you know, z to z0. It has to be along a path, but all the same, if you'd like to write it like that, that's totally fine. You could do like a straight line homotopy or something if you wanted, since this region is very nice, right? The upper half plane has, it's convex, in fact. So also, just to be clear, the principal branch is used for the powers in the integrand, since complex number to power is relative to your choice of the branch of the logarithm, since we define a to the b, if you don't recall, as e to the what? B log a? Or a log b, right? Anyways, you remember the whole business. Sorry, I'm not trying to take away from this presentation of the theorem. But yeah, principal branch used for the powers in the integrand, and each of the following hold. These are the interesting pieces that'll make it all kind of tie together. So two of the points x1 through xn minus 1 can be chosen arbitrarily. A and b are determined by the size and position of P. So think about the b is just shifting it and the a is just scaling it, right? So if you have this shape, but maybe it's too small, you just grow it to be the right size. And if it's in the wrong place, you just move it over to be in the right place. Okay. So that's what the A and B's do. Basically, it's saying that this piece right here gives you the right shape, just maybe in the wrong place or maybe the wrong size. All right. So determine the size and position. Okay. F of xi is wi for I from 1 to n minus 1. And f takes the point at infinity to wn. Notice, that's interesting. W1 to n minus 1. Huh. So notice, there are 5. W1, W2, W3, W4, W5. And I only have x1, x2, x3, and x4. Because the point at infinity is getting mapped over to W5. If you draw this in the Riemann sphere, it looks a little bit nicer, and it seems like it makes a little bit more sense, actually. So just think about what the old Riemann sphere looks like if you can tolerate my horrible drawing of a sphere for a moment. So here in my terrible drawing of a sphere, we have 0 down here. We have the point at infinity up here, right? Okay, and the upper half plane. Where is this living? This is the circle of radius 1, you know, this mod z equals 1, right? So this is like, it's kind of harder to draw this if you guys will allow me to draw it this way. It's oh gosh, it's so hard to draw some things. It's like everything like over on like half of the circle. You see what, or on that sphere, right? I mean, really all you have to think of is it's like a hemisphere of the sphere. All right, so you can imagine pretty easily looking at this whole business that you could, you know, along like the real axis or something, right? There's going to be some points, you're just deciding where to do the bends. And one of those points has to be up here at infinity, right? Because you have to do a bend up there or something. Otherwise, you'll end up with like a curved piece. So that's why you have to use that extra point up there. And bada boom. So there you go. And that's the whole business of how we're doing it. We're just putting some like, okay, here's like a X. Oh, sorry, I should use a different color. Here's like X1, X2, maybe X3 and X4, and here's that point at infinity. So you can kind of imagine that like as we take this region, we could sort of put our bends in so we can make that like nice shape. Oops, sorry. You get what I mean, right? And then maybe it comes out so it's not quite in the right place, and then we just scale it to the right size and we move it to the right place. All right, so it's a Schwarzkristoffel transformation. It's a pretty neat little fact that you can actually create this thing directly, right? It's kind of cool. All you have to do is go, okay, what are these outside angle coefficients, right? What's the outside angle divided by pi? If you look at the angle as being between minus pi and pi, all right, then pick some points that you want to go to the vertices, and then pick the vertex you want to go to infinity to go to, right? And then bada boom, do it. Easy. Kind of neat. Okay, so that's pretty much the. No, if you notice, we're not doing exactly too many proofs right here. This is more just conceptual. I don't need to see that you can do a bunch of algebra to deal with these kinds of things. I trust that you can. You're, mature mathematically at this point in your careers. You have, displayed that well enough. So this, dealing with all of the whole, okay, do the Mobius transforms take the right things to the right places? It's a lot of manipulating symbols, right? It's just a lot of algebra. And if you're cool with doing that, then the important takeaway is the conceptual piece about saying, hey, I can use transformations, I can use Mobius transformations, fractional linear transformations, if you want to call them that, to take circles to lines, circles to circles, lines to lines, that kind of business. And it's a useful trick. It's the only way to map a circle to a circle, pretty much. In fact, the open disk to itself, right? It's the only type of conformal map from a disk to a disk. Oh, all right, cool. Then we also have an example of how we could get a little bit fancier. That's pretty much the only role that the Schwarzkristoffel formula is going to serve for us. It's just an example of how you can do fancier things. It is important for other reasons in other parts of mathematics, but for our purposes, it's basically to say that, hey, there are other accessible types of conformal transformations, and indeed we could actually do a lot of examples even with relatively complex shapes, and these things are not that hard to get at directly. Now, what I want to touch on briefly while we have time, and since this is going to be a much longer and more interesting and more fun section, is the idea of analytic continuation. we will be able to talk about some fun stuff. And I think that this is one of the neatest parts of complex analysis, because it just truly highlights how interesting and restrictive analyticity, holomorphy, whatever you want to call it, is. What this whole notion of satisfying the Cauchy-Riemann equations plus continuously differentiable, why that constraint is so powerful, and just how much it gives you. It's honestly, it's like kind of ridiculously OP. Like it's super overpowered in terms of how many results you get out of this sort of stuff, and this fact is probably one of the ones that gives you the most, that most clearly highlights how insane of a punch that simple requirement gives you. So, analytic continuation. The basic idea here, and this, get ready to wrap your heads around this, because this just blows my mind. When I first, it doesn't matter how many times I see it, it still always like makes me go like, it seems like it should be wrong, but it's amazing and it's neat, and it shows how rigid this class of functions is. So the basic idea, I'm not trying to cross that out, I'm trying to highlight it. The basic idea is that if two analytic functions agree on a small portion of a connected region, this is nuts, then they agree on the whole region on which they are both analytic. Okay. Just let that sink into your mind for a minute. It says that, hey, you've got function A living over in this world, and you've got function B living over here, doing some stuff. And, here's like a little chunk where they overlap right on that little section, right? If they are the same here, like if F is living in here and G is like living in here or something, if like F is equal to G here, then F and G are the same all over through here. Whoa. What? Now let's get into this a little bit more, because there are some caveats that we should be careful to talk about, but the idea is actually kind of nutso, and it gives us some actually incredibly wild stuff. So Theorem 6.1.1, the principle of analytic continuation, the identity theorem. So let's let F and G be analytic in a region A, okay? Now let's suppose that there's a sequence Z1, Z2, Z3, a sequence of Zi's, right? Of distinct points in A, distinct points, converging to some Z0 in A, such that F of Zn is equal to G of Zn for all n's, right? So for all elements of these sequences, these two analytic functions agree. Okay. Then F is equal to G on the entire region A. This conclusion is valid particular if Fn is equal to G on some neighborhood of some point in A. So notice this is actually stronger than the piece we said before, which is like, hey, on a neighborhood if they agree. This says it doesn't even have to actually be like it doesn't have to be a neighborhood. It just has to be a single sequence of points. What? Like, that should just blow your absolute mind. Like, I can come up with like real functions all day long that are not the same but agree on sequences of points. Like, that's nuts. Convergent sequences. But holy cow, it's amazing. Why is it true if F is equal to G on some neighborhood of some point? Well, because a neighborhood of a point contains an open set. That point is inside of an open set, right? There's an open disk about that point contained in the set for it to be a neighborhood, right? Like if you have a neighborhood of a point, that means that there's an open disk centered at that point that is inside of the set we're calling a neighborhood, because that's what it means to be a neighborhood. All right. So if you have an open disk, then certainly every sequence of points in that disk going to the center, there are very many of them, are all in there, and if the two functions agree on that disk, then they'd certainly agree on all of those sequences. So this is in fact stronger this one just about sequences and having equality for these sequences, provided the sequences converge. This is actually stronger than the neighborhood piece, but most people tend to say these, give the example for analytic continuation is like, oh, if they agree on a neighborhood, then they agree on all of A, right? Okay, cool, easy. This is neat. So it's kind of a wild thing. How could this be true, and how will we prove it? Let's start getting into it. So idea is going to be simple. We'll let h of z be equal to f minus g. Then h is certainly analytic on A. That's the difference of two analytic functions. Okay. And h of zn is 0 for each n, because these two guys are equal. F of zn is equal to g of zn. That's our assumption right here, right? Okay. What we want to show is that h is equal to 0, since that will mean that f is equal to g, right? We'll show that that's true for all z and a, and then f will be equal to g for all z and a. Now, way back, I kind of stressed this a little bit. Corollary 3.2.10 on the local isolation of zeros of a non-constant function tells us that h of z is equal to 0 on some open disk around z0. Okay. Now, the connectedness of A will allow us to extend this conclusion to all of A. Ah, okay. So, it's equal to 0 on some open disk around Z0. Okay. Extend it to all of A. To this end, we'll let B be the set of Z and A's such that H is 0 on a neighborhood of Z. Then B is a non-empty subset of A, since Z0 is in B, right? Because H of Z0 is equal to 0, right? Or sorry, H is 0 on a neighborhood of Z. Z0 is in B, right? Should be Zn. Yeah, well, Zn is absolutely in there. We can if you don't want to do anything more complicated, it ultimately will be true. It'll be true that h of z is 0 for all z, so it definitely z not will be in there, but I believe the textbook meant to say zn, since we just said that right up there. Certainly z0 is in there, but all of them are in there, right? So okay, now if w is in B, then h is 0 on an open disk around w, obviously, contained in A, of course, and hence on a neighborhood of each point of that disk. Thus, that disk is contained in B as well. So if you have a single point inside of B, then you have an entire disk of points inside of B. Of course, this means that you could grab any point in that disk, and you could get a disk around it, and so on, right? Okay. That means that every point inside of B has a neighborhood around it that's in B as well, right? Okay, so it's open. If every point has a if a subset has a neighborhood of every point in it, then it's open, right? It's open. Okay, open subset of A. On the other hand, let's suppose that W1, W2, W3, so on. This is a sequence. These Wi's are distinct points in B converging to a point Z in A. Then, of course, h of wk will be 0 for each k, since h is 0 on entire neighborhoods of every point in B. So definitely it's 0 on every individual point in B. So it's equal to 0 for each k. And since A is open, Z is interior point, right? Okay. So these points converge to some point. It is going to be an interior. Okay. So corollary 3.2.10 applies again to show that h is 0 on a neighborhood of this limiting point. Thus, z is in B as well. This shows that B is closed relative to A, right? Does that make some sense? So just think about it real quick. if you don't remember the idea of closed relative to something, it's the subspace topology. This is going back a little bit. So remember, if you have a topology, this is on a set S, right? This is a collection of subsets that we call open that satisfy certain nice axioms, and you could grab any subset of that thing and form a topology all of its own from the original topology by just intersecting those open subsets with the subset you've chosen, right? So if you've got, you know, like S, and then you have like your topology tau, right? Then if you have some S prime contained in S, you can form tau prime as let's call these subsets O, intersect S prime such that O is in the original topology, right? And then you get a new, if this is topological space, then you can form this new topological space, ST prime, and that is it's the subspace topology on S prime. That is this topology. You derive a topological space, a subspace, from this topological space by just taking the topology and basically cutting it down to the piece you're actually dealing with, right? Throwing away all the stuff that lives outside of S prime. Okay, so we say open or closed relative to something, we mean open or closed in the subspace topology. So B is closed relative to A means that B is closed in the subspace topology of A as a subset of the complex plane. Okay, so we've shown that the subset B is both open and closed relative to A and is not empty. Since A is connected, the only subsets that are both open and closed relative to a connected set are the entire set and the empty set. It's not the empty set, so it's the entire set. If you want to see this, we proved this back in 1.4, or at least discussed it. It's 1.4.13. So h of z is equal to 0 for all z and a as we required. This is crazy. So think about this. This is useful for a lot of reasons. There's exactly one analytic function on C that agrees with e to the x on the x-axis, the real axis, right? You know, namely e to the z. Huh, okay, cool. Why? Because the x-axis contains a sequence of convergent distinct points. For example, 1 over n, right? You know, as n goes to infinity, this goes to 0. And of course, that's in the domain of e to the x, right? So this it tells you that our notion of e to the z that we came up with very early on like the first day or second day, this guy is the one analytic function on C that agrees with this. Kind of cool, right? Neat. Okay, it'll also give us some much crazier and more interesting stuff. For example, you could be interested in a function like like this, or even, sorry, I should write, I'm gonna make that a 1. How about, sorry, that's a 1. Maybe erase that, make that like cleaner. 1 to infinity, 1 over n to the z. This is a well-known function. It's a Riemann's zeta function. And of course, this guy converges for certain z's, but for other z's, it doesn't, right? Okay, so what gives? Well, it converges on a nice open subset of the complex plane, an open connected subset of the complex plane. And we could find, perhaps, as we'll see, a function that is analytic on the entire complex plane, or on like large parts of it, and we can find one that is analytic on the entire complex plane that agrees with this guy on that domain, and hence is like a unique extension of this thing to values that don't otherwise make sense for us to actually plug in. And so this is where you'll see things that are like, like this, like, 1 plus 2 plus 3 plus 4 plus da 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 da, equals like, what is it, like -1/12 or something, right? I think it's negative 1/12 or something. What is it? This is zeta of -1. What is it? Don't just remember these all off the top of my head. Yeah, it's -1/12. And so you like to see people like write stuff like this and be like, whoa, math is crazy, or like those mathematicians are lying to you. They've played us all for fools. Like, we know that this isn't true. Just count with your hands. But this is just going to be a shorthand for saying, hey, what is this function that does make sense for certain values agrees with some other thing that you can make up a function that agrees on a bigger subset, right? You will be able to essentially take this guy and extend its domain to things where this form of expressing it is not the appropriate form. Now, what the appropriate form of expressing it is, and this is where it gets kind of cool, may not be something that we can very easily access, but we can say that the thing exists and that we can even get some information about what certain values are. And so, of course, this is like what will end up being the case for like zeta of -1. So we're not saying that this is actually true. This is not true, but it's this function here that will basically extend. It's a notion called analytic continuation that we'll talk about next time. We'll be able to extend it to something where it does make sense to plug -1 in. And the reason we'll be able to do it fundamentally just boils down to the argument of this right here, the principle of analytic continuation. So it is, however, very important, though, that we take some caveats into account. It is very vital that A is connected. If A consists of, say, two disjoint disks, the function that's 0 on one of them and 1 on the other one would agree with the 0 function on the one part of A, but not on the other, right? Oh, okay. So you need to be careful on certain things like that. Connectedness is quite important. Okay. Now, remember as well that a region is an open connected subset of C, so it's an open connected subset. Okay. Now, Corollary 3.2.10. I'll pull these guys up at the start of next class because we're going to use them more, or at least we'll reference their intuition more. The local isolation of zeros. We'll be able to extend this to a global form on connected sets, and this is the corollary we'll go through next. After that, we'll get into a lot more fun and interesting things. We'll define what an analytic continuation is. We'll talk about lots of other pieces involved in this and some things we have to be very careful with. But at the end of the day, what we'll get this just utterly nutso result, giving us a true host of just unbelievable consequences of incredibly far-reaching importance. So let's leave that there, and I'll see you on Wednesday and on Friday, and then I won't see you again. So please email me now if you have any questions. All right, have a great night. Bye.